Welcome back. If you're looking to get smart fast, you're in the right place. Today we're diving into something pretty innovative.
Indeed. We're looking at stochastic computing, or SC, and specifically how it can be implemented directly inside memory using ReRAM.
ReRAM, that's resistive RAM.
Okay, so stochastic computing. It's not the usual binary approach, is it?
Not at all. The core idea is representing numbers differently. Values between 0 and 1 become probabilities in random streams of bits.
Probabilities. How does that work in practice?
Well, think of a sequence like, say, literal 1 to 1. That's 5 bits, 3 of them are 1s. So it represents the probability 35, or the value zero point 0.6.
Huh, interesting. And this different representation, it changes how you do math.
It simplifies it, actually. Multiplication can become just a simple logic A and D operation on the bit streams.
Just an A and D gate. Wow. What about addition?
Addition often uses something like a majority logic gate, or sometimes an OR gate if the inputs are within a certain range, like 0 to zero point 0.5. Subtraction and division are also possible, though a bit more complex. Okay, so simpler operations. What's the big win here? Is it just speed?
Speed is part of it, but a huge advantage is fault tolerance. Because it's probabilistic, single bit flips in the stream don't drastically change the overall value. All bits have equal weight.
Right, unlike binary, where flipping the most significant bit is catastrophic.
Yeah,
That makes sense. But generating these random streams, hasn't that been a challenge?
it has. Traditionally, you'd use CMOS-based pseudo-random number generators, PRNGs, and comparators. But these can be, well, power hogs and take up significant chip area, sometimes up to 80% of the system cost, apparently.
80%. Wow. And then you have the issue of moving all those bits around, right?
Exactly, the classic von Neumann bottleneck. Shuttling those bit streams between the memory where they might be stored and the processor where the logic gates are, that costs time and, crucially, energy.
Which brings us to this specific research. They're tackling this bottleneck head-on using ReRAM.
Precisely. They're proposing an all-in-memory approach. Do everything, generate the streams, perform the calculations, get the result, all within the ReRAM array itself.
So tell me about ReRAM first. What makes it suitable?
Well, ReRAM is a type of non-volatile memory. It stores data based on high resistance for a 0, low for a 1.
Advantages.
It offers read speeds comparable to DRAM, potentially higher density, and lower energy use for read operations.
But it's not perfect, right? I remember hearing about drawbacks.
True. Writes can be relatively slow and energy intensive. There are limits on how many times you can write to a cell endurance issues, and its behavior isn't always perfectly linear or predictable.
But maybe that unpredictability isn't entirely bad here. And the fault tolerance of SC you mentioned, does that help with ReRAM's reliability issues?
That's one of the key ideas, yes. SC's inherent robustness can help tolerate some of ReRAM's imperfections, like its nonlinearities.
Okay. So some people have tried combining SC and ReRAM before, but this paper goes further.
Right. Many existing approaches still use CMOS for the random number generation part, which, as we said, is a bottleneck. This work aims to eliminate that dependency entirely.
So the mission today is to unpack how they manage this full integration. How do they generate random numbers in the ReRAM?
They leverage a property of ReRAM itself. The switching process, changing between high and low resistance, has an inherent randomness, a stochasticity. They figured out how to harness this to generate true random numbers directly within the memory cells.
Using the device's physics. Clever. How do they turn that into the stochastic bit streams needed for computation?
That's where their in-memory stochastic number generation, or IMSNG, comes in. They basically compare these internally generated random numbers against the binary input data.
Compare them how? Inside the memory array.
Yes, using bitwise logic operations performed within the ReRAM itself. Specifically, they implement a greater than comparison using sequences of in-ReRAM XOR and AND operations.
That sounds potentially write-intensive, though, which you said is a drawback for ReRAM.
They thought about that. They propose two main strategies. One is IMSNG naive, which uses a feedback loop in the peripheral circuitry to reduce the number of actual writes needed.
Okay, reducing writes. And the second one?
Is IMSNG opt. This one goes further by using latches, also in the periphery, to minimize writes even more. It's about being smarter with the intermediate results.
And does this in-memory generation hold up in terms of quality? Are the random streams good enough?
According to their results, yes. They compared the mean squared error, the MSE, against software methods, standard PRGs like LFSRs, and even quasi-random generators like Sobel sequences.
Hmm.
The IMS-NG methods achieved comparable accuracy, especially for longer bit streams, like 64 bits or more. So it seems viable from an accuracy standpoint.
Okay, so we have the streams generated in memory. Now, how do they actually compute with them still using ReRAM?
They use a technique called scouting logic, or SL. It's its way to perform Boolean logic, A or not, etc., using ReRAM read operations.
Read operations, not writes.
Mostly reads, yeah. It involves accessing multiple cells at once and using a specially modified sense amplifier to interpret the combined result as a logic function.
And this is efficient.
Very. Basic gates like NAND, NOR, XOR, NOT can apparently be done in a single clock cycle using this method.
Wow. So how does that translate to the stochastic arithmetic we talked about earlier, multiplication, addition?
Well, multiplication is just that A and D operation, right? So with SL, they can do a bitwise A and D across many bits in parallel, essentially multiplying the stochastic numbers.
In one cycle.
Potentially, for the core logic, yeah. Scaled addition using that majority gate can also be approximated with a single cycle SL operation. Even division, which is trickier in SC, they implement using latches built with SL components to form a JK flip-flop circuit.
So it's bulk bitwise operations happening in parallel right there in the memory array.
Exactly. This massive parallelism is key. It can significantly cut down the latency compared to doing binary arithmetic sequentially, or even compared to moving stochastic streams to a separate processing unit.
And again, how does the accuracy look for these in-memory SC operations?
They check that too. Comparing the MSE for various arithmetic operations using different random number sources, including their IMS-NG, the results showed that doing the SC operations in memory with IMS-NG streams gives accuracy that's comparable, sometimes even slightly better, than using traditional random sources but computing outside the memory.
So generate in memory, compute in memory.
Yeah.
What about getting the answer back out? You need a standard binary number eventually.
Right, the stochastic to binary conversion. Their method is pretty neat. They use bit-line kern accumulation.
How does that work?
They take the output stochastic bit stream, the result of the computation, and apply it as voltages to the word lines of a special reference column in the ReRAM array. All the cells in this column are preset to a low resistance state.
Okay.
So when a 1 from the stream hits a word line, current flows through that cell. When a zeroth hits, little or no current flows. By measuring the total current sunk by the entire bit line using an analog to digital converter, an ADC.
You essentially count the number of ones in the stream.
You got it. And that count directly gives you the binary representation of the probability encoded in the stream, all done in a single step, effectively.
That's quite an integrated system. Did they evaluate the overall performance? Energy, speed?
They did. They used simulations, integrating their models into tools like NVMain. They tested it on applications like image compositing, which uses multiplexers, bilinear interpolation, and even image matting, which involves division.
And the results? How did it stack up against, say, binary compute in memory or the traditional CMOS-based SC?
Okay, let's talk energy first. Compared to a binary compute in memory approach, their ReRAM-based SC design used, on average, 2.8 times less energy.
2.8x less. That's significant. What about versus standard SC?
Compared to the conventional CMOS-based SC system, where you have the PRNGs and data movement, the ReRAM approach was about 1.15 times more energy efficient on average.
So better than both. Mostly because it avoids moving data.
Largely, yes. That off-chip communication in the CMOS designs really adds up in terms of energy cost, though they do note for very large image resolutions, the CMS approach might sometimes edge it out, perhaps due to the overheads in ReRAM becoming dominant at massive scale.
Interesting nuance. What about speed or throughput?
Similar story, the parallel nature of the ReRAM approach paid off. They saw about 2.16 times higher throughput compared to binary compute in memory, and 1.39 times higher than the CMS-based SC system on average across their benchmarks.
Faster and uses less energy. That sounds promising. But what about reliability? ReRAM isn't perfect, as you said.
This is where SC's inherent nature really shines, remember? They specifically tested how the system performed when they introduced faults, like cells getting stuck in the wrong resistance state, mimicking ReRAM unreliability.
How did it compare to, say, doing the same computation using standard binary methods within the faulty ReRAM?
The difference was stark. For the traditional binary arithmetic running in the faulty memory, they saw a huge drop in output quality measured using things like SSIM and PSNR for the image tasks. An average quality drop of around 47%.
Nearly half the quality lost.
Ouch.
And the stochastic computing approach.
With their proposed ReRAM-based SC, The average quality drop under the same fault conditions was only about 5%.
5% versus 47%.
Uh-huh.
Wow. That fault tolerance isn't just theoretical then, it makes a real practical difference, especially with less reliable hardware.
Absolutely. It suggests you might not need complex and costly error correction or fault protection hardware that you typically need for reliable computation and memory, especially for ReRAM. SC provides a level of built-in robustness.
So, wrapping this up, the key takeaway seems to be that this all-in-memory stochastic computing using ReRAM offers some pretty compelling advantages.
Definitely. We're seeing potential for significant boosts in throughput and energy efficiency, particularly attractive for edge devices or embedded systems where power is tight.
And crucially, that inherent fault tolerance makes it a good marriage with maybe less than perfect memory technologies like ReRAM, potentially lowering overall system cost and complexity by reducing the need for heavy error correction.
Precisely. It's a synergy between the computing paradigm and the hardware
It
characteristics.
really makes you think, doesn't it? This tight integration of compute right into the memory fabric. What other kinds of complex tasks, especially in energy-starved intelligent systems, could benefit from this kind of stochastic in-memory approach as these memory technologies continue to evolve?
That's the forward-looking question. As ReRAM and similar technologies mature, this kind of thinking could really reshape how we design efficient AI and processing systems at the edge.
Definitely something to keep an eye on. For anyone wanting to dig deeper, the source paper has all the detailed comparisons and methodology.
Yes, exploring stochastic computing and in-memory processing concepts further is certainly worthwhile. It's a fascinating area.
Great stuff. Thanks for walking us through that.
My pleasure.